Thank you very much, and good afternoon, everyone. I'm very happy to be here and to speak about this topic, AI and quantum computing. So I have a double challenge. It's to speak about two important topics in 10 minutes. And also a challenge is to explain these topics after the lunch. So double challenge here. So you will understand that I will not deep dive into quantum mechanics. And I'm happy about it, to be honest. And I will not explain how a computer works, a quantum computer works. And the reality, if I'm really honest, if you do AI, data engineer, data science, AI scientist, or whatever, your daily life is you import a library in Python, like scikit-learn, PyTorch, or TensorFlow. You feed data into a machine learning algorithm, and you get the results, and you move on. Quantum computing and artificial intelligence work exactly the same way. You import the library in Python, the quantum machine learning library. You feed with data your quantum machine learning algorithm, and you get the results. So that's what I will explain so far. So my objective is to tease you. In 10 minutes, I just can't do this. And to tease you is we have been working with banks and financial institutions since a couple of years now, developing algorithms, IPs, use cases, and so on. And we know by design that these algorithms will make, let's say, a competitive advantage to this institution. So I think it's really an important topic that should be taken. And I know that several of you are already working on it. So why quantum? Let me give you an example, a simple example. We'll do some math, sorry for that. But everybody here knows how to do a multiplication. So if we multiply two numbers, two integers, big ones, and you will get this n, it will take, let's say for a normal computer, 0.0025 seconds, which is pretty quick. And if you take a quantum computer, it will take 75 seconds. So at this stage, you can say quantum computers, it's okay if you want to use it for multiplication, but it's not really useful or it doesn't really worth it. But let's take the inverse operation, find the two integers that does n. For a normal, let's say, computer, it will take 4.7 billion CPU years. What does it mean? If you want to count the total operations to do this simple math, it takes 1 million operations per second. You multiply it by 60 seconds, by 60 minutes, by 24 hours, by 365 days, by 4.7 billion, and you get the total number of operations to do this simple math. What does it mean? It means that with a classical computer, you cannot do it. Even with all the innovations we will have in the couple of years, by design, you cannot do it. And the funny thing is that it's pretty easy. It will be pretty easy with a quantum computer. It will take a few hours, few minutes, depending on the machine, evolutions, etc. But it's very quick. So one message is, as you know, this kind of computation is within the cryptographic algorithms. So we talk also about quantum safe. So it's important to know that in your IT, maybe you have algorithms that can be a problem, and we have solutions to handle this in the world. But most important is quantum is able to do stuff that classical computing cannot do. A few examples: you have very hard problems that a classical computer can handle, maybe today or in the future. Easy stuff that we handle already today, and things that they cannot handle, and it's easy for quantum computing. So quantum is not really a better version or a faster version of classical computer, is just another paradigm that we have to take into account. And it's if we have to define it, it follows the law of nature and represent data in ways that mimic the randomness and unpredictability of the natural world, things that GPUs and classical computing cannot do. And when I say randomness and unpredictability, we can cite some example in finance that maybe certainly you know about it: stock market prediction, trading, option pricing, risk management, market simulation, and so on. Many use cases that are already that you worked every day, let's say, and you can handle this with several solutions, including AI. So we have very typical algorithms that can handle this. So support vector machines, neural networks, or GANs. And when you look at them specifically, for those who are not really familiar with, for example, support vector machine, this is very simple, actually. Let's say that you have yellow points and blue points, maybe turquoise, but let's say blue, and you want to separate them. So what you do is that you calculate a margin, and you try to maximize this margin and draw a line between the points. And then when a new point is coming, if it's coming on the left, it's a yellow point. If it's coming on the right, it's a blue point. Very simple. The problem is that if you cannot separate the data, so imagine you have these points, if you draw a line, a linear line, you cannot separate them. Okay? If you put the line between the yellow and the blues, you will have a problem, and the same on the right side. So you cannot separate them. And what you do is you apply a function, what we call a feature map, that will add another dimension to the data, and then with this new dimension, you can separate the data, and you have another algorithm. We do exactly the same thing with quantum computer. Quantum computing, you apply what we call a quantum feature map. So you transform your data in order to be able to separate it. And the difference is that you leverage quantum characteristics to find a better pattern within the data. So what is the difference? The difference is we published a couple of papers since a couple of years now, from theory to application. And the first thing we demonstrated is that when you have a hard problem to classify, and one well-known problem in mathematics is the use of discrete logarithm problem. Look at this. And then when you use this kind of algorithms, you do not classify the data in a very good way. You do like random classification. It's the same accuracy. And when you use quantum support vector machine, you can solve this problem very efficiently. So what does it mean? This is generating synthetic data. So this is theory. But at that time, it gives us the point that you can find patterns with quantum where you cannot find patterns with classical computing. So that was a first clue. Then we saw that we can provide exponential speed up about the machine learning. And then what is important is not really the amount of data, but the complexity of the data. So the conclusion of these papers is what? When you have very complex data, and randomness and unpredictability or complex data, quantum computing can be another alternative to find patterns and to better classify the data. And of course, from theory, we applied it, and you have many examples about application on the classification of data where quantum do a very good. So I encourage you to see these papers. Same for neural networks. I'm not going into the details, but what we found clearly is that we can handle high-dimensional data, and that we can train the neural networks with what we call lower losses and faster. What does it mean? You get the results quickly, faster. So when you speak about Gen AI, everybody knows that Gen AI, behind Gen AI, is neural networks. So we know also that the computational power needed for the Gen AI is a problem. It is a problem in terms of availability, money, sustainability. And some of the companies that are looking to Gen AI and are creating models, they are also looking to quantum computing as an alternative. So that's also things we can do. And of course, GANs, what we call generative adversarial networks, which means that you can generate synthetic data to improve your machine learning models or AI, or also learning and loading random distributions, which is well known in the financial services world. It's just a couple of examples, but in 10 minutes, really my main message is look at it. You can already test it. As I said, you don't need to be a real expert in quantum mechanics or quantum computer. You have just a couple of libraries to import and use it. Take your data, feed your algorithms, and test it. And you will find in the literature a lot of use cases, as I already mentioned, in financial services. Done. 10 minutes. Thank you so much, and I hope you enjoyed the presentation.
Julien?